decay stuff. We're going to cover that when we probably next week or the week after. But just so you know, it's that neutron and protons kind of leaving those atoms, and so that's kind of what that ends up being.
Yeah. You're so rude. Shut up. I got muted.
Hi.
We're muted, right?
Oh, I can't hear you. Hello, hello?
Hi.
Did I just unmute it?
Oh, it's just delayed.
Is this other guy evidently is presenting right now?
There's two guys.
Yeah, that's the other guy that we can't. That's in his office there. That I'll tell him. Sure, I think you like carefully.
No.
Whoa!
That's good.
Oh no! It does.
No sound yet.
Yeah, they should just.
It's just like, yeah.
Just bring a particle reactor.
We're still live, folks. I think they probably can hear us. Can you hear us? Well, we can't.
You're done, you're done.
Yeah. So,
Did you call us?
Yes, we did. Hi.
oh.
No, we can't hear you. No, that's. Just, you can hear us, presumably.
I like your guy. Oh, that's his name was.
Okay, try.
You're on. You're off.
One on, and we're gonna give this a little bit. Okay, can you hear this one?
There we go. Yes.
Holy cow! Why? I don't know. All right, fine.
Okay. Good.
Can you see Hendrik?
Yes.
Oh my gosh!
Hello there.
Hi.
And you can hear me.
Yeah.
Very good. So are you guys ready
This
to
is
go?
complicated.
Yeah.
That's so
Okay. And we have two classrooms, right? Both?
Yep.
Okay, so I'm really happy to do this today. I hope it will be a little bit interesting. I'm Hendrik Schatz. As you may have figured out by now, I'm originally from Germany, but I've been in the States for a while. So I hope my accent is okay. I'm a professor at Michigan State University, and I'm currently the director of the Joint Institute for Nuclear Astrophysics. And I just love to talk about my research, and I thought that's what we're going to do today. I prepared some slides for you to look at. And now comes the challenge. We got to switch over.
Yeah.
How we do this?
So you can. the screen share there and say entire screen and share. And it's going to do this freaky thing. Isn't that cool?
This is amazing.
Hey,
Okay,
nice.
so it's about the universe inside of you. And I don't know, do you see the mouse pointer here? So here's the universe, and here's you. And the interesting thing is that this is actually true. So there's a piece of the universe inside you. I have to be careful with my mouse. And that's what we're going to talk about. Before I do that, though, you may wonder what this Joint Institute for Nuclear Astrophysics is. It has this wonderful logo at the bottom of the screen. I don't know if you see that. And we sponsor a lot of the outreach events. And I'm just going to give you a quick slide. So the interesting thing what we're doing is we're getting scientists from different fields together. We're getting astronomers here. We're getting people doing computer simulations. We do actual experiments in the lab here downstairs at Michigan State University and other places. We do people that do theory. And it's a large group. It's not just at MSU. It's multiple institutions across the US and actually across the world. I think 22 institutions are networked together. So it's a really big thing. It's really exciting. And I'll tell you a little bit about what we're doing. Again, astrophysics and nuclear physics. Now, I don't know if you guys talked about all the exciting programs we have for students like you guys. So you should go to the JINA website and check it out. And we're actually working at an upgraded website that will be even cooler. But yeah, check it out. There are lots of programs and activities, including, and I'm sure your teacher has already told you about this, the PAN program for high school students. I just thought I'd throw this slide up here, show you how typical scientists look like, just to give you sort of an idea. So these are typical research groups here at the lab, you know, professors and grad students, and we also have undergrads working here, and occasionally, as part of the PAN program, high school students come into the lab and do the same research that we do. And this is currently happening at the MSU site and the Notre Dame site, and there are kids coming from all over the country, so that's maybe something to check out. But you can see we're having a lot of fun doing research. A little bit obvious from those pictures. Okay, so let's talk about atoms. I don't know, did you guys talk about atoms in class?
A little bit. A
little bit. Good. Okay, so you may know that you're made of atoms, but how many are there? So this is an easy math thing. Sorry, I got to start with some math. There's, assume, you know, 70 kilograms or 155 pounds of a person. That would mean about 6.7 times 10 to the 27 atoms. So that's really a lot. Here it is. Okay, so it's pretty unbelievable. And the reason, of course, is that atoms are really, really small. Now, I don't know if you know how small they are. Anybody know? Okay. Well, now you're really curious, I think. So, I don't know, the next example is a bit weird, but we were sort of thinking about something really small as an example. And someone came up, I don't know who that was. You know, the thickness of a fingernail. That's something you can imagine, right? Yeah, here it is, the thickness of a fingernail. You would be able to stack up 10 million atoms on top of each other across that thickness. 10 million. I take it that the silence is awe. Very good. Now, the nucleus inside the atom, right? There's a nucleus and the electrons around. The nucleus inside the atom is actually almost 100,000 times smaller than the atom. So that's a pretty crazy small thing. Okay, but it turns out that that little thing determines pretty much how the universe looks like. Anyways, now you are made of atoms, and here's sort of your typical composition. Of course, you know, it depends what you ate in the morning. And, but so roughly, you're going to have a lot of oxygen, a little bit of carbon, hydrogen, and then all these other elements in your body. And they're obviously very important. So the science question that we're dealing with here is, where the heck do all these atoms come from? Now you may say, that's a stupid question, they're just there. But anyways, it's a really good question. If you look at the history of the universe, so this is here early, the first thing that happened was the Big Bang, right? And then time evolves to the right. So imagine you're a chemistry student or a science high school student at the time of the Big Bang. And the teacher tells you to learn the periodic table of the elements by heart. It would actually be a pretty easy task. There it is. So this is the periodic table of the elements. I'm sure you've seen it, right?
Yeah.
You've seen that. That's at the time of the Big Bang. So now you obviously wish you lived back then, right? Life was much easier in high school. So they're just three elements: hydrogen, helium, and lithium. So two gases, and I guess lithium is a solid metal. No liquids, so that's maybe not so much fun. But otherwise, things are pretty good. Anyway, so just three elements. That's how the universe started. But now today, I know you probably have that on your wall in your classroom. Today, the periodic table of the elements looks like this. So all these elements have been made somewhere along the way. And that's what we're trying to figure out. Okay, so now I want to take some shortcuts here. We're actually concerned with the origin of each single element. They're all precious to us. We all like them. But I'm not going to talk about those elements that are covered up here because we understand pretty well how they're created. They're actually created in stars, which merge elements into each other, create new elements. What I want to concentrate is all these other heavy elements, what we call the heavy elements. And you see, there's some interesting things here. For example, gold. I'm sure everybody likes that. Platinum. Where do those elements come from? They're obviously here on Earth, so they have to be made somewhere. But it turns out that's actually an open question. It's actually one of the 11 greatest unanswered questions of physics. And that's what we're trying to figure out. Okay, so, well, we do have some ideas. But before we go there, I just want to talk a little bit about how we imagine the process. Okay, so first of all, we got to recap a little bit. I just want to make sure we're all on the same page. So, did you guys know that the nucleus is made of protons and neutrons?
Yeah.
This is not news, right? I don't know. So here it is, right? So protons are red usually, neutrons are blue, and you just pack a bunch together of each, and that's an atomic nucleus. Now, who knows what determines which element this is?
A little louder, guys.
Protons.
The protons, very good. The number of protons is the element, and the neutrons are just there to, you know, for the fun of it, making different isotopes. Now, have you guys seen the chart of nucleus ever before?
No.
Oh, good. Well, oh, now it works. Here it is. So what we're doing is, going back again, we're just counting the number of protons, 1, 2, 3, 4, well, and so on in this nucleus, and then we count the number of neutrons, okay, and then this nucleus this particular nucleus lands on this table somewhere. So this is the number of neutrons, this is the number of protons. So let's say there were 16 neutrons and 12 protons. So we go here to 16 neutrons, and then we go up to 12 protons. Can you see that here? Right? Oops. Okay, 12 protons, 16 neutrons. This little sphere, that's that nucleus. Okay? So each sphere here is a different nucleus with a different number of protons and neutrons. Isn't that cool? How many nuclei you can form? I mean, it's amazing. Now, who knows this number of protons, right? So this is the element. Who knows what 6 protons, what element that is? Yes. Oh, you guys are amazing. So this row here, these are all carbon atoms because they all have 6 protons, right? They have different numbers of neutrons, so they're different isotopes. Now, who knows what these gray squares are?
Stable.
Yes, I think I heard it. Those are the stable isotopes. So not all of the possible nuclei actually occur in nature naturally. So only the gray ones are stable. The open ones here, you can make them, but they're going to decay. Some decay within hours, some decay within minutes, some within milliseconds. So these are radioactive isotopes. Okay. Okay, so are we on the same page here? It's pretty straightforward, right? Okay, so now this is not the whole table. Here are a few elements. This is not even the whole table, but it's pretty much most of it. Okay, so there are many more elements, of course. Does anybody know the element number of gold? It's a hard one. 79. So where's 79? Can you go up here? See this row here. Those are all gold atoms. There's only one stable one. So there it is. So this whole row is gold, right? This row is mercury. And you know, we can add and subtract neutrons and make different isotopes. Or we can add protons and make different elements. Okay, are we good so far? So now here's how we think nature makes new elements, the heavy elements. It's called neutron capture, and it's pretty straightforward as a concept. So imagine you have a nucleus sit around, maybe inside a star, and imagine there are lots of neutrons flying around. And occasionally, the nucleus captures a neutron. Okay? Okay. Now, this is a little piece of the chart of nucleus, right? So this is the number of protons, number of neutrons. And let's say we start with this nucleus here. Now, this nucleus now captures a neutron. So it will become a different nucleus on this chart. Right? Which one? So usually now I think both. I don't know. Teachers, can we figure out what the preferred color is in the classroom? Are there any teachers?
Yeah, there's teachers in both rooms.
You guys?
Neutron, what color do you get? Oh.
Do you guys understand the question?
Yeah.
Or the middle
Blue.
square.
This nucleus will capture a neutron, and it will become one of the other nuclei. Which one?
Blue.
Red.
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 Okay, there was a lot of blue, but now I think red wins. Is red winning?
Yeah.
Yeah, red is winning. Very good. You guys are good. So you add a neutron. The number of neutrons is here to the right? So you add a neutron, so you make this nucleus here. There you go. Okay? So we make a little arrow, and we transformed one nucleus into another. Now that's great, but some of you may now ask, did we actually create a new element?
Yeah.
Did we create a new element?
Yeah.
No.
No, we didn't. Because the number of protons is the element, right? We just added a neutron, that doesn't help. You haven't accomplished anything, really. But we're not done yet. Okay? So this nucleus may be radioactive, and if it's radioactive, it will beta decay. Okay, so did you guys learn about beta decay?
Yes.
We did! Hey, that's amazing. So you know that a neutron switches into a proton?
Yep.
Oh, so then where does it go? Which color? I need to give you some colors.
Yellow.
Yellow.
Yeah, I think I heard a lot of blue. That's good. You guys agree? Yes, blue. Okay, well, so this nucleus, okay, sits here in a certain number of protons and neutrons, and now one neutron is converted into proton. So one neutron disappears, right? So it goes to the left, and instead one proton is added, goes up here. Now, did we now create a new element?
Yeah.
Yes.
So that's how it works. We add neutrons to make it unstable, and then when it decays, hooray, we have made a new element. And I mean, that's a bit of a convoluted way to make elements, but that's apparently what nature is doing. Okay, so now we're ready for almost the real thing. This is a real chart of nuclides now. Okay, and one hypothesis is, and I'll tell you later what the possible site is in the universe. One idea is that the process that makes the heavy elements starts with iron, and these are the iron isotopes here, and these are the stable ones. So it starts with stable iron, and it so happens that there are a lot of neutrons around, and there are actually tons of neutrons around. The typical time to capture a neutron is 100 milliseconds. Now that's very fast, right? 100 milliseconds, like snap. Okay, so now I ask a lot of questions and colors, and yeah, I just need to see what you guys think. So we go step by step. So there's iron and neutrons. Now what happens, you think, after, let's say, we wait for a few minutes? What will happen? Oh, here are the colors. The neutrons around, and typically it takes 100 milliseconds to capture a neutron. So once we waited for a few minutes, what will have happened? Red, exactly, red. A neutron has been captured for sure after 100. It only takes some milliseconds, so if you wait a minute, for sure a neutron will be captured. So that iron 57 here, 57 protons and neutrons, will be converted into a different iron isotope, right? What happens next? Color? Red. Why not? Right. I mean, it's going to capture. There he goes. Now we're coming into a range of the unstable isotopes, right? So those will not wait around forever for a neutron to be captured. They will eventually decay. Now, these numbers here, that's the typical half-life. Did you guys talk about half-life?
Yeah.
Okay, great. So this is about how long it takes to decay. So this one has 44.4 days. So what do you think it will do? Will it decay first, or will it capture another neutron? Red?
Yeah.
Yes, right? I mean, 44 days before it decays, so if it only takes 100 milliseconds to capture a neutron, for sure it'll capture another neutron first. So there we go. Now this one lives a million years, 10 to the 6. So for sure I'll capture another neutron. I go a little bit fast if that's okay. Yeah, I usually have flashcards or something, then it goes a bit faster. Anyway, so 6 minutes. The M means minutes. So what do you think? Keeps going or decay?
Keeps going.
Still going, right? I mean, 100 milliseconds is really short. So, gee, it keeps going. It keeps going, right, until it reaches an isotope that has a decay half-life that's comparable, right, to the time it takes to capture a neutron. I hope that makes sort of sense. And, you know, as you go along the line, that will happen sort of here. So now this is interesting. What do you think this will do? It's iron-68. It has a half-life of 100 milliseconds. So it takes roughly 100 milliseconds, and then it decays. But it also takes still 100 milliseconds to capture a neutron. So which one will happen? It's a trick question. Okay, what do you think?
Are you talking about one atom or a bunch of atoms?
Yeah, good point. Let's pick one. What's it going to do? Well, you don't know, right? It's a random process. It's like throwing dice. It could go either way, right? Now, if you have 1,000, where will those 1,000 go? So roughly half will decay and half will capture a neutron, right? Equal likelihood. Yeah. So they're basically throwing dice, and both will happen. Okay? Sometimes they'll go this way, and sometimes they'll go the other way. And there are lots of iron nuclei around, so some go that way and some go that way. Now it's interesting. If you go here, then this is actually longer lived again, and you have to go back. You have to go again until you go to an isotope that decays before it captures. And here, 89 milliseconds. Now that's shorter than the time to capture a neutron, right? And so that for sure will decay most of the time. There's still a small chance it go the other way, and will happen occasionally, but most of the time this will decay. Now, if you look at the other branch here, these guys, that's 180 milliseconds. They will probably capture a neutron, and they sort of merge here, and then they'll capture, they'll decay 90 milliseconds. That's 1.6 seconds. That's long. They'll capture a neutron. You know, it goes on like that. It's sort of a pattern. And each time there's a decay, it goes up and left, right? Sorry, it goes up and left. Each time that happens, a new element is created. Right? So we're going from iron to cobalt to nickel to copper to zinc to gallium to germanium. Okay? Now, this doesn't help too much, though. Now we've made all these things that say in a star, these isotopes, but they're not the isotopes that the Earth is made of, right? These are the stable isotopes. So what will happen is eventually the process stops, and all these isotopes will just beta decay until you reach the stable isotope. Okay? So that's pretty cool. So if you look, now this is maybe a stupid example, but I don't know, is there any germanium in your classroom? Does anybody have a piece of germanium by any chance? Well, maybe not. Anyway, so if there would be germanium in your classroom, it would be made of these isotopes, but these isotopes would be the decay product of a really exotic, rare isotope that is radioactive, and it has been created in a star, and then it has decayed to be your germanium in your classroom. And the same thing is true for gold, for all these other heavy elements. They have been made as radioactive isotopes, and then they decay. Okay, so where does it happen? Now, does anybody know what this is?
Star.
That's a star. Does it look familiar? It's a famous picture. So usually, you know, you look at the stars one night, and then the next night you look again, and they're still there, right? Yeah, mostly. But sometimes something happens, and here's kind of, this is one day, one night, and the next night it looked like this. So the star exploded. That's the famous 1987A. I don't know who saw that. Probably nobody, because actually I don't know how you guys are here.
They were.
That's one problem. The other problem is it was only visible on the southern hemisphere. But anyways, so isn't that cool? Star explodes. And you can see that with your naked eye. This is the supernova explosion. And we think that the process may happen inside a supernova explosion. Here's a nicer picture of it. Now I have a little movie how this may come about. And I hope you like it. I'll just play it. So the star explodes because there's a core of iron in the center that's just too heavy. And it starts collapsing. And eventually it gets so hot that the whole thing explodes. And oh, wait. Do you see that? Yeah. That's really lighter. Go back. So you see all these iron nuclei? The star has worked very hard to produce in its lifetime. Now the supernova just rips through it. The explosion just rips through it. Well, maybe I should. I'm not going to run it. This is not my usual computer. Anyways, yeah. So the supernova rips through them and destroys all these iron nuclei. They're just protons and neutrons again. But now something weird happens. The iron core becomes a neutron star and it emits neutrinos. I don't know if you've heard of those particles. And look what those neutrinos do. They convert protons into neutrons. That is pretty sneaky. So you started with roughly half protons, half neutrons. But now the neutrinos create lots of neutrons. And now it cools, the stuff gets ejected into space, and new nuclei form. See, protons and neutrons find each other, and then those find each other, and in the end you build again nuclei that have roughly equal number of protons and neutrons. But there are all these extra neutrons around that didn't find a partner. And they are now getting captured in that process that I just described to you. So this is how this looks like sort of in reality. I mean, in animation, and not on this chart of nucleus. Did we miss the beta decay? Okay. So the neutrons get captured, right? And then at some point, the decay is faster than the capture of the next neutron. There you go, and a new element is created, and that's sort of how it goes on. So inside of an exploding star, that's for the current working hypothesis. There's only one problem with this. Well, do you guys want to see the real calculation? Do you guys want to see real science?
Yeah.
Okay, here it is. Remember what we did on the chart? We went sort of step by step, and we looked whether it captures a neutron or decays. Now, I actually took a computer program that works that out for me. Okay? Started. This is the chart of nucleus. We start with iron here. You see the color red means there's a lot of iron. And we just let it go, and it calculates for me whether the neutron capture wins or the beta decay. And you see how all these elements are created actually in very short time, within a few seconds. And then, as those elements or isotopes cool, they decay. Now use the beta decay. They just decay back, and eventually they become the stable isotopes. Okay, so that's happening during a supernova explosion, and all that stuff gets ejected into space. Eventually, it forms a new planet, and then people on that planet look in the ground and they find these isotopes and say, "Hey, there's gold. That's good. That may be useful." And then, you know, scientists figure out where that thing came from, and then that's exactly what happened. So the Earth, your bodies, everything is the product of a supernova explosion that happened a long time ago, and everything's formed out of that material. Now, there's one problem with all this. And I don't know, I can go back. You see all these numbers on this chart? Right? Okay. I now have to admit that most of these numbers are not known. Now you say, gee, what is he talking about? Does he know anything? Well, there are theorists that try to predict these numbers. How long does the nucleus live? But they can be off by many orders of magnitude. They can predict it takes 10 milliseconds, and in reality it takes 100 milliseconds. So that's the problem. All the calculations I showed you are actually, they may not be true. We don't know, because we don't know what the properties of these nuclei are. So now this is bad, right? So what are we going to do? What would you do? There are two options. You can throw up your arms and say, well, okay, just let's give it up. We'll never figure this out. But we're scientists. We figure things out. And so we just go ahead and ask the government for a lot of money. And we build an accelerator that can make all these nuclei. And so we can measure those numbers and put them in, and then, the calculation may actually go completely different, and it may not work, or maybe it works much better, we don't know. And that thing is actually being built right now at Michigan State University. It's called the Facility for Isotope Beams, or FRIB. And here's a pretty recent picture of the construction site. So it's happening just next door. It's a $730 million project, and it will be completed in 2022. And we're extremely excited about it because for the first time it will allow us to make the same nuclei that supernova make. And we'll figure out all these questions. Now, I think I should probably stop here for questions. Okay. Zach says I should show it. I made this animation because now you're probably wondering, well, how can you build such a thing? How is FRIB making these isotopes, right? That's what everybody's wondering now. Yes.
Yeah.
Good answer is yes. So here's how. So it turns out it's extremely difficult to do the same thing that stars do. So of course we could just get some iron, put it into a place where lots of neutrons are, and then let it go. Problem is nobody has any idea how to make that many neutrons because they actually decay, so you have to make them fresh. So we just do the opposite. So instead of starting with a light nucleus and building things up, we start with some heavy nucleus like uranium, and we accelerate it. There it goes. We accelerate it to about 50% of the speed of light, which is pretty fast. And then we slam it onto a piece of carbon. And what happens? Well, it just falls apart. Right? In this case, we got 3 pieces. And these are 3 different isotopes, right? They will have the protons and neutrons from the uranium, but distributed differently. And most of the time, nothing interesting will come out of this. But, maybe once a day or so, or once an hour, there'll be an interesting nucleus that we need to study. And we have a separator here that separates the good from the bad and sends it to the experiment. And then these nuclei, you remember, the half-lives are like 100 milliseconds. So we have to do a really quick experiment and measure, for example, the decay or the mass or whatever we need to know. Okay, so in 2022, that's what we're going to do. I'll leave it at that, and I'm happy to answer some questions you may have.
Questions? Are stable isotopes always generated in the stars from the neutron side of the stability curve?
I heard the first part. Are stable isotopes produced in stars?
Generated in the stars from the neutron side of the stability curve? it looked like they were all being generated as a result of beta decay.
Yeah, this is a very good question. Most of the heavy ones beyond iron are. But if you look on the chart of nuclides, you actually see that there are some isotopes that are sort of outliers, and there's no way to get to them. Right?
Yep.
And those are made, there are other processes that are happening to make those. So there's actually quite a number, if you look at the textbook, there are 3 processes of heavy elements. The S and R process, and I only talked about the R process. The S process is actually also a neutron process. It's equally important, and the P process makes these outliers. We actually have no observations that show that there may be more processes going on, and it's a bit more complicated. So, yes, there's a lot more happening than just decaying from the neutron side. You can also decay in research. Okay.
What's the half-life on a neutron?
It's about 10 minutes. So that's the problem. So they have to be made fresh somewhere. And I sort of brushed over another difficulty that we actually don't quite understand how supernovae can make so many neutrons in such a short time. Yeah, we need more questions.
We're looking into the questions about the stars, but could you relate to us some ways that this relates to us in everyday life as well? The answers to these questions, besides basic research of how the elements are formed, these elements in our body and the star formation.
You mean how it relates to everyday life?
Right.
This basic research. So the result, like, hey, supernovae make heavy elements, only affects you intellectually. I mean, if you're interested in science and you love to read science stuff, then that's fine. There are a lot of practical applications in the end that come from basic science, as you probably know. Most of the interesting things around you have started with basic science. For example, we came up with building this machine because we want to create those isotopes that we need to study to figure out the big questions. And that's why people from all over the world come to MSU and they pick their brains and come up with this difficult facilities. And now once we have that facility, we can actually do a lot more. We can, for example, search for new isotopes for medical applications. You can pretty much make any isotope you want. So if you're a medical researcher, you may want to have certain diagnostics to track processes in the body, and you need an isotope with very specific properties. Right? It has certain chemical properties, it has a certain decay radiation, a certain energy, and with the Effort facility, you can basically pick that out of, because we have such a big range that we can produce, and we can send you a sample.
My bad.